Hi guys, Tim's back again. Hope you can see me all right. What I'm going to do now, this is for AS students I suppose, although A2s can certainly look at it of course, as per usual. I'm going to give you an overview because I think I've pretty much reached the end of the specification as much as I'm able to. Halo alkanes being the last sort of thing that I've delivered through these the online tutorials and that sort of thing. What I want to do now is do an overview of the whole of organic chemistry at AS and how it all fits together, if I possibly can. The exam board produce these sort of things. I don't know whether you can see them, but they're a sort of an overview sheet. I'm not that keen. They don't really give you a great deal of help, but basically this is for the whole of the A-level organic chemistry. But if you look, you've got AS alkenes, AS halo alkanes, AS alcohols, primary, secondary and tertiary, and then the line gets a bit blurred between AS, so I'd say that maybe that corner was AS, but it blurs into A2. Halo alkanes are a starting point through nucleophilic substitution for amines, reaction with ammonia, for example, and amines with halo alkanes, nucleophilic substitution, reaction with the cyanide nucleophile to form nitriles, okay. Yeah, and then you can extend the carbon chain to form carboxylic acids, or we know this from a nitrile, or you can hydrogenate to form amines, but with one extra carbon in the chain. From alcohols, this is when it gets blurred from AS to A2. You can go, you can oxidize them to form a ketone if it's a secondary, to form an aldehyde if it's a primary. This is pure A2, where you have an aldehyde or a ketone, nucleophilic addition, guys, to form the hydroxynitrile, because you always form that. You always get that OH when the double bond breaks, the C double bond O breaks. That's totally familiar to you. Going down here, sure, oxidation product, fully reflux, carboxylic acid, and those feed into A2, so it's all interconnected. Carboxylic acid from a nitrile, A2. Carboxylic acid to an ester, AS and A2, you know that. Acyl chlorides are probably a bit of a side issue, but they are sort of derivatives of carboxylic acids, and you can make primary and secondary amides from those. So that's got a certain value to it, but what I'd like to do is pull out the AS and give you a bit of a revision summary on where we're at and all that. But don't forget, I'm now starting, yes, I'm giving you packs to do, but I'm also giving you specific past papers, AS students. So I'm giving you one, which is because now you should be able to go for the whole paper, breadth and depth, and the organic chemistry questions contained within. You should be able to do a paper properly. You do a paper under exam conditions. I will download you hopefully the mark scheme for that through emails, and then you self-mark and you see where you went wrong and you learn, because I will be checking. Okay, make no mistake, because you could get a little test maybe. Who knows the way things are going to pan out. So if you haven't done any of this, you haven't got a clue, you've had it. Okay, we don't want that to happen. So make sure you put some effort in to learn this stuff. Right, here's a quick overview which may help you. I might even get my red pen out for this. Let's see. Right, overview. Call it AS Organic Summary. I can't even spell. Okay. So my version, more specific about what you need to know. I suppose the starting point will be alkanes. Okay. What do you need to know about them? Well, they're fairly boring from a chemist's point of view, but they undergo. Let's put a little box around it. Let's get the lovely colours out. So alkanes, first family. Right, what do you need to know about them? Right, you need to know that they undergo combustion. Incomplete, complete combustion. You need to know that the naming of them, the idea of, you know, alkyl groups, branching, naming of branching. Boiling point. What affects the boiling point of alkanes? Points of contact, the more branching, the lower the boiling point. Remember that, because there's less points of contact, so there's less intermolecular forces, therefore lower boiling point. So how the structure of alkanes affect their physical properties, namely boiling point, done all that. Okay. Another one that you need to certainly know about is, and this is the hardest, free radical, homolytic fission, a mechanism, right? Remember, initiation step. You know, I don't want to put everything on here, I don't want to teach it. Right? For an example, I for initiation, P for propagation, chlorine free radical bumps into whatever, I don't know, keep it simple, methane, to form another free radical, so methyl free radical, and a product, HCl. Okay? Don't forget there's an overall equation at the back of this. Termination might be, well, there's another, really, propagation, always 2 steps. So, what's the other one I always get wrong? So I've made a product there. This one, methyl free radical generated in the initial step, plus a chlorine molecule from earlier on. Guess what? Makes a product, chloromethane, plus regenerating the chlorine free radical. And your termination, you know, free radicals coming together to cancel each other out. And don't forget, you can have this, you can extend the chain. So this is very, very quick. I don't know why I should. Very quick. 2 free radicals can make C2H6. That's sort of an extreme example of those 1, 2, 3 steps. You know all that. That's absolutely fine. This could get quite busy, but it don't matter. Right, now, cracking, which we haven't really looked at, but basically you're taking out hydrogen. If you take out hydrogen from an alkane, you're going to form a new family. You're going to form alkenes. Because these things, they're great for fuels and stuff, but they're not very useful from a feedstock point of view to make lots of other chemicals from. So these come straight from crude oil, and they're cracked to form alkenes, which is a far more interesting molecule, or an interesting starting point. And again, I'm using the families here, alkenes, but it's about the carbon-carbon double bond, not about necessarily it being an alkene. It's got a carbon-carbon double bond, it will do these sort of things. Right, so what do? Sure, they undergo combustion, the same as alkanes do, and you should be able to do a balanced equation for that. Then they do quite a lot, okay? Probably the biggie is halogenation. Right? What's all that about? That is about electrophilic addition. Right? Where basically you're adding Br2 or Cl2 or I2 or HBr, which can have implications for Markovnikov's rule. Okay, Markovnikov's. Which side of the double bond does the H go? Which side does the Br go? We've done all that. I'm not going to start talking about Markovnikov's rule now. Okay, but you should know that the H goes to the, what is it? The carbon of the double bond that already has the most H's on it, so that you go by a more stable carbocation. Primary, secondary, tertiary carbocation, favoured product, favoured route. Done it all. okay? And that's nasty. You know, the devil is in the detail. The high marks are the nasty questions. This overview, you won't pass anything, but it gives you an idea of where we're at. And then you break it down by doing specific nasty questions, and that way leads to success, okay? Right. I'll come down to those shortly. So you've got those, halogenation. Then there's loads of others. So you've got like hydration. Right? You've got halogenation, hydration, hydrogenation. All of these we've done. Hydrogenation allows me to go back. Hydrogenation plus H2, that's a nice symmetry, to form your alkane again. So there's a lot going on there. But of course, let's look at these in turn, because hydration. The addition of water plus H2O. Okay, steam, catalyst, phosphoric, concentrated acid, or sulfuric tends to be mentioned, concentrated. Okay, and don't forget what would, right, bang that way, dehydration. A big deal here. There's a lot in this, minus water. That's our link to the next step, the next stage. So if you hydrate, you form a whole new group called alcohols. Okay. Right there. If you hydrate, it's absolutely specific. You've got your carbon-carbon double bond there. You are going to open it up and put an H on one side and an OH on the other. Okay, so you specifically put one OH on when you're hydrating a molecule as water adds across the double bond plus H2O. So you're into a new family. You're making an alcohol. That alcohol might be primary, secondary or tertiary, and that might have implications later on, but once you're making an alcohol, you're into a whole new group with all the different questions that get asked about that. But I specifically want to talk about dehydration, because don't forget, sure, when you dehydrate, you take away the OH, but you might have, well, probably will, an H either side of that OH, so you could remove the OH, either that one or that one. In other words, the double bond can end up in there or in there. So you could end up with at least two different products if the double bond goes in there or the double bond goes in there when you dehydrate, or a third product, because one of these might have stereoisomers, cis-trans isomers. So you've got to be aware of that. There can be at least three products there. We've met questions on that. They're a higher level. You need to be able to do them, no problem. It's hardly difficult. Just where are you taking your H2O out, and what implication will that have for the alkene that you form? Structurally different, stereoisomer different, whatever. We've seen questions on that. They're all over the place. Okay, so, you know, you've got to be clear on all that sorts of stuff. Now, we can go in a number of directions here, but we'll go down this quite important one here. Oxidation. Using acidified dichromate. And if it oxidizes, you get a colour change from orange to green. Okay, but it will only oxidize, as you well know, if you have a primary alcohol. Okay, and then if you distill, you get an aldehyde. So you're into more the A2 realms here. You get an aldehyde. Okay, orange to green, sure, you get an aldehyde. You've got to distill the aldehyde off. Always remember your laboratory techniques. There's a new family, and of course reflux, so I should put distill there. Reflux, carboxylic acid. secondary, these are just terminology, as you well know. Distill, reflux makes no odds, ketone. Okay, but of course, you've got to be able to draw these out, you've got to be specific, you've got to go into complete. This is an overview, right? Ketone, no problem. Tertiary, a completeless, nothing. Zero, nothing. Resistant to oxidation with dichromate. So once you get those, and remember, you're into the realms now of this sort of thing. Now, making this up, but basically carboxylic acid, I don't know, let's have a look at a simple one here. Simplest, ethanoic acid. Remember, there's quite a lot of questions on this with spectroscopy questions where you have an unknown. So, you know, you're looking for that type of... See, did you spot my deliberate error there? No. There. Okay. You're looking for that sort of thing to tell you it's a carboxylic acid. You're looking for the clues to tell you it's a carboxylic acid. You're looking for the colour changes. You're looking for the percentage composition. You're looking for the mass spec to see what the overall molecular formula of it is from the molecular ion peak. You're looking for the infrared. Do you have a carboxylic acid group, or is it just an aldehyde or a ketone, C double bond O? Okay, or do you have a broad peak for OH? You've got to look at all these clues and use your knowledge of chemistry to deduce these unknown things. We've spent some time on this, but there you are. And again, you have to watch it, because you might say that this unknown here, right, was reacted with an alcohol. Maybe the alcohol's up here somewhere. Okay, maybe the alcohol you went down there and it's reacted with the alcohol you started with. Either, but immediately you should know that you had an alcohol. So I'll put alcohol where? Acid catalyzed H plus ester. I want a bit of red there. Bloody hell. So you're looking for that. Two products is the clue. One being the ester, the other one being water that's eliminated from the molecule. So there's a whole sequence of questions there to get your heads around in terms of spectroscopy and analysis that, again, we've looked at. Right, so that's okay. Let's go down this a bit. Let's look at, so we've done hydration to make alcohols. Let's go down here. This is Br2, HBr, right, across. You are going to make a whole new family, haloalkanes. Okay, because you're going to add across the double bond. Okay, haloalkanes, there they go. Right, so what are you going to get? There's your alkene there. Right, so maybe you add across it like that. Maybe if it's HBr or HI or HCl, maybe you add across it like that. Right, following Marconi-Coles rule. I don't know, HBr across there. Either way, you've made a haloalkane. So whether you made one or whether you start with one, you end up with this here. CX, X-chloro-bromo-fluoro. But what matters is delta plus delta minus there, because that makes it vulnerable to nucleophilic substitution using a nucleophile. Now, I've discussed this in previous videos about nucleophiles, but perhaps we'll just keep it simple on this. Hydroxide nucleophile, bang, bang. Guess what you're going to do immediately? You complete the loop. You're into alcohols. Okay? Now, how do you recognise how you end up with the alcohol formed by this route is different from the alcohol formed by that route? difficult to say, but this one will only put one OH on. If you've got two BRs here, you can put an OH on both. Okay, so you could get two OHs on, but that's not a hard and fast rule. Either way, you end up with an alcohol group there. Remember, these have different rates, and there's an experiment called hydrolysis, because the reaction of this sodium hydroxide, it's aqueous sodium hydroxide is the reagent to produce your hydroxide nucleophile. Okay, so you can take three different haloalkanes, as I've shown you before, and you can monitor the reaction by the halide that's kicked out, that's substituted, reacts with silver ions, and you can see how quickly they precipitate. And remember, basically the question is this: why does an iodo react faster than a bromo, which reacts faster than a chloro? Answer: because the carbon iodo bond has a lower bond enthalpy than carbon bromo, than carbon chloro. Okay, lower bond enthalpy, therefore less energy is required to break it, therefore the reaction is faster. Those sort of questions come up quite a lot. And don't forget, with haloalkanes you also need to bear in so rates of hydrolysis, gotta know that. And the ozone layer, have a look at that. You've got books and stuff, but I've given you a video on it. Sort it. Okay, so all encompassed within that topic. Okay. Now, arrow going up that way, so we're talking on there sodium hydroxide aqueous to make your alcohol from your haloalkane, but also you can go the other way. You can take an alcohol, and with this can be confusing, but you can use HCl, and I've touched on this because we're making a haloalkane. I've shown you a video on that where we take an alcohol, and again it's nucleophilic substitution, but going in the other direction using either HCl, or you can use KBr, KCl with acid to generate your halide nucleophile. I don't want to confuse you on this, but it's entirely and utterly the reverse mirror reaction of going that way. So, and I've shown you a prac on this because we're supposed to make a haloalkane, but just to quickly for completeness, if you've got your COH there, from here, your alcohol, right? Nothing to stop nucleophilic attack from maybe a chloride ion. It's a nucleophile. Bang in there, bang in there. Okay, back to your haloalkane with OH. Mine, the result of those two arrows will of course be CCl. So it's a total reverse that way to that way. Students find that a bit confusing. I don't know why. It's because I haven't looked at it properly. It's not confusing, it just sort of completes the circle. So there you go. That's a sort of overview, an overview of AS organic chemistry. I hope it helps you a bit, but like I say, the devil's in the detail. The only way you're going to do well is to look at those nasty questions in the pack and sort them out. So the haloalkanes pack is your starting point. Make sure you understand the spectroscopy. I've given you the packs for that. I've given you hopefully the stuff for that. You should be able to sort that yourselves. But there you go. That's the overview of organic chemistry. I don't think I've forgotten anything, but there'll be plenty of other stuff I can do anyway to sort of focus on that and see where we're at. Okay, thank you guys. Chin up. Have a good Easter. Holidays, it's a bit weird having a holiday now. I sort of can't quite get my head around it, but have a good Easter. Work hard, do some work, progress, move forward. Okay, that's the way to do it. Okay, do some stuff, learn some stuff. You'll feel a lot better if you do. Anything else to say? No, I don't think so. I'll see you soon. Ta-ra.